Welcome to the presentation from the Industrial Internet Consortium about protecting Internet of Things IIoT endpoints. This is a radar recorded presentation which originally held on Industrial Internet Security Forum at Sunnyvale, California at October 6, 2016. My name is Marcellus Burkheit. I'm President and CEO of WIBU-SYSTEMS USA. This is a quick overview about what we're talking today. At first, when we talk about security of endpoints, we should clearly understand what is an endpoint. Then the next question is why we need security of endpoints. And when we have defined that, then we break down this very abstract word security to specific functions in an endpoint. And the last part of this presentation talks specifically about implementing of endpoint security, which can, of course, in this 20 minutes, we have only a short overview. When you look to the IIoT landscape, you have something similar you see here. You see in the front here the edge, which is connected to devices in the operational, which needs a physical closeness. And then we have an area we're still discussing about the right name. It's a computational network. Some people say it's still the edge, other people say it's core, or it can be the relatively new word is the fog, which is behind this edge. And then we have somewhere virtual, far away, somewhere, the cloud computing, which is relatively new in the whole industrial area. But where are now the endpoints? There are some people that say, oh, the endpoint is easy, they're just the devices, that's the end of this network. While other people say, no, the endpoint is actually that what the edge connects to this network behind. Or you say, the endpoint is maybe the cloud computing access where all the networking really leave our area and goes in deep in the internet. Other people said actually the computational network is already the internet when you connect virtual connections and other stuff. So that's the endpoints. And some people also say the end of that is in the cloud. So what's an endpoint? I was very confused the first time I heard this word. So it's time to clearly define that. The IISF, the Industrial Internet Security Framework, and also IIC, which stands behind the IISF, defines endpoints very similar like the ISO IEC standard says. An endpoint is one of two components that either implement and exposes an interface to other components or uses the interface of another component. That sounds really bizarre and a little difficult. And we thought it's for industrial, business-oriented security understanding too difficult. So we simplified this sentence, and you can see our definition in the IIC vocabulary document version 2. Endpoint is a component that has an interface for network communication. That sounds very easy and very simple. So it's practically says whenever you have a communication and communication ends somewhere, there's an endpoint. And we added a little clarification in this vocabulary. An endpoint can be of various type. It can be a device, or it can even be something in the cloud which provides cloud connectivity. So to simplify, we have an abstract model. You have a communication channel, and the end of this communication channels are two endpoints. So we have for my accent, I'm from Germany, and we have in Germany a joke, or is also a wisdom about our culture. So we say everything must have an end, but the sausage has two. So not just the sausage, it's two. So whenever you want to think about what an endpoint is, just think about communication in the internet, in the network, has two ends named endpoints. So come back to our landscape. So where are now the endpoints? They are everywhere. So it's not restricted to any location. Don't forget the word end assign with any location. It's just the communication. And what is so interesting about this? We have now one model where we can explain all security practically on any point where some code is running, some computer execution happens, some data is stored, because all these things are the ends of communications. So it is also important that a single computer, even a single device, can have several endpoints, because they have then several communication points. Give you an example. A router has usually a LAN endpoint and a WAN endpoint, and they from the communication totally independent. Of course, they are connected to function as a router. And you have frequently, and the router is a good example, shared code and data between multiple endpoints, which make the security not easier, but this is something you have to address. And there is also, of course, communication between endpoints with security of this communication. That is another model. I'm not talking in this presentation. There is another presentation at the same event which talks about that. The interesting thing is that the endpoints are the only location in any even extremely big IIoT system where execution code is stored, started, and updated. The data is stored, modified, and applied. We define such data which is stored at data at rest, and data which is modified or used at data in use. The communication to another endpoint, even when we don't talk about the communication security model, is still initiated and protected and also executed in an endpoint. And the other presentations we will hear later here, we're talking about security, analyzing, configuration, monitoring, and management is finally code, and this code is also executed in endpoints. So a result is, if ever an attack happens, it typically starts in attacking one or more endpoints. Hackers are usually very smart people, but they're also lazy. They not analyze your whole network to find the point of attack. They look very strategic and very smart to the weakest position, and this is usually in the implementation somewhere in an endpoint. There can be a very stupid, dumb device, but this is poorly implemented, and from this stupid device you can address your whole IIoT system and attack it, and no one ever would thought that this device was the weakest point until the hackers show you this. So if this is done, then another technology is usually very effective, is get the execution code in an endpoint and try to modify it or even replace it to make a malicious attack. So this is practically when the hacker hijacks the endpoint to do something else. And there is many other options and many other possibilities I not want to talk today. We come now to the endpoint protection model, our security model. This is a part, this picture is from our security framework document. So the overall security starts, you need an endpoint security model and you need a policy. So you have to define how your security works and which reasons it should be affected. On this model, we put our data protection model. So the data protection is still a very abstract understanding. So there is data and there has to be in any form protected against modification or just addressing when it's about keeping data secure. Then we have the physical security. We cannot talk about any software implementation when we not address that the whole device can be opened physically, can be stolen, can be remotely damaged or something else. So physical security is a very essential first step. We come to the root of trust. The root of trust just says who defines that this device executes code which controls my code has a trust. Because otherwise, when an update or something coming in an endpoint, for example, no one would know if this is really the endpoint I want to address, or this update is accepted by something else which checks about trusted code. So that is all the root of trust in the very bottom. Then we need an identity who says, yes, this device is has a specific function, a specific feature, a specific behavior, and to guarantee this, I need a specific identity. And we have more things, well, I'm not talking today. It is more about what we hear in future sessions today. So we talk about the access control, we talk about the monitoring and analysis, and we talk about the configuration management. So you need, when you have security, you communicate with other devices, you have to set up that. And this has to be simple, configurable, it has to be managed, maybe remotely, and it has to be also monitored and analyzed if it works correctly. And the last point, we also not talking much today, is an integrity protection, which means your code which is executed, your whole system, your data, is everything is integer as a whole system and cannot be partly modified to make attacks or damage something. An example, that was very abstract, this model, so I give you here a little more an example how in the practice, in a real physical hardware software combination named endpoint and a device or a computer or anything, the vulnerability starts. So we have, for example, the hardware components. You see this here in the very bottom, which has definitely, we have to, for example, be sure that the processor is valid, is not replaced by something faked, the memory is correct, the peripherals not able to leak data, for example. And then we come already in the boot process. The boot process is extremely critical because when someone fake but for malicious attack, the boot process, then everything else but later executed, the core of the endpoint, can finally be replaced, can be a fake, can be used for hijacking by the hacker, by the intruder. The same thing happened with the operating system. Are we sure the operating system is secure, it's correctly updated, it runs as intended? Again, you have the same issue with any hypervisor, with any virtual core, or even if you don't use an operating system, when you do execution direct from the core, from the BIOS, is this valid? I give you an example. There's a lot of systems, they have a virus checker that runs outside of the operating system in a checking mode of the device. And when this virus checker would not be trustful and valid, they could replace the whole code which runs later again in the normal mode, and no one would find it out. So don't think just about the operating system in your own code, think also about other codes which runs in this endpoint. And then finally the core, the applications. The API can be vulnerable, not just the code. For example, the API can accept illegal parameters who would be used for a buffer overrun or something else, and your security is already in danger. We have the whole runtime environment with libraries and other containers, which is from third parties. So you have to think about also when you integrate code from other people to simplify your development, is this trustful? Finally, a very important point is the deployment. Who guarantees that the installation and the update, the start of the whole system, can be trusted? The data we already talked, so we have the data at rest, the data at use. When data is uploaded from outside, is be guaranteed that this data is trustful? Is it sure that the data cannot be addressed if it's not permitted, and so on. The monitor and analysis, I'm not going details, that is later. Same with configuration and management. But overall, you have it can also be that your security model or your policy is incomplete, is poorly developed, and then everything which depends on that, of course, is not more secure. And the development environment is the last thing I mentioned here. When you use compilers, when you're using any libraries, be sure the latest version is trustful, and so on. I come now to some points how you can make your endpoint security bring on a high level. So the first important thing is start with the clean design of security models and policies. The Industrial Internet Security Framework talks a lot about that you see how such models can look and what these policies are. For example, defined the clear identification for the endpoint, talk about the authorization and the authentication. So authorization, identity means how other endpoints see me, and authorization means what they can do with me. So which commands can they send to me and how I answer. Is this trustful? Is this secure? Can this be compromised? These things you are addressed at a high level. Then use a clear, clean, proper data protection model. You have to provide integrity and confidentiality for data, especially when it's shared data in rest or data in use. Shared means, for example, it's on a memory stick or on a SD card, which can be physically removed from the device or from the system, from the endpoint, can replaced with someone different, and this could be a fake data, and that could be used for any attack when your code permits some weaknesses and you not provide integrity. Define your hardware as secure, especially the BIOS, because if the BIOS is fake, everything later can be executed as illegal. And very close to that is the root of trust. So the root of trust is usually located in the BIOS, or if the BIOS is based on the root of trust, or the BIOS represents the root of trust. But if you think about you have BIOS updates, then you have to be sure that this root of trust cannot be compromised. You should also think about, when you talk about hardware, this is now a little beyond security. This is also beyond reliability. You have a long lifetime of your product, especially in industrial systems. Is it sure that this hardware can be replaced with the same or with some updates which are still trustful? And so we come sometimes away from just in the moment it works secure. You have also to see the whole life cycle of your product. Finally, when your software will hardly run alone beyond the BIOS. You have usually an operating system. In complex system, you have hypervisors. We can give you very nice security boundaries, but you have to implement them well. Is your programming language supporting security, or it's more offending security? This is something you have to discuss with developers. Define also if your compilers in your libraries can be updated. when you have open source, it's great. You can principally make your own updates, but you need someone who understands this open source. Otherwise, has no value for any upgrading. And expect also the dynamic of programming languages. Is my programming language still available in a couple of years when new security demands are required? And consider isolation principles. We explain in the Industrial Internet Security Framework document 4 different models, because isolation is a very powerful, easy to implement principle to guarantee security in the critical areas. Finally, have a plan for update your code remotely and provide code integrity. You must understand that any code, and this is not even code, this is even code which is very professional, clean, developed today, can be vulnerable tomorrow. So security has always an expiration date. The only problem is you don't know when it is. But when this code is vulnerable, you need an update, and this update can only work efficiently when it's remotely possible. And for this we have the internet, the industrial internet, to make this simple. But when also other people can update, not just you can provide a new update, then we're running quickly in this code hijacking that the hacker prevents that he has an update which is in reality malicious code. So you need code security to provide this update in a secure manner. And plan beyond the basics security. So don't just think about, I have it clean implemented, it works great, and there's no errors. Think about that also the configuration and the management of security should be user-friendly. It should be easy. For example, think about when you're using keys or certificates that they need sometimes replaced, or even design a replacement mechanism, a replacement plan, or even updates them frequently to provide higher security. All this is beyond the basic security, but it helps that your system can be used in a manner as you intended it. For example, when you talk about monitoring and analysis, it is a very good idea when you log all security configuration changes or all expected, maybe malicious remote activities, but it doesn't help when you have just a very, very long log file with million of lines or million of characters in many thousand lines. It should be any user-friendly analysis possible. For example, if you provide in XML with a simple tool to show where really the critical illegal accesses happened. All this is inside of monitoring and analysis. That's what your product make finally from some side of the user more secure as you originally maybe had expected. And implement always state of the art. Have an experienced security team. Software security or information security is something which will be very seriously taught today in universities. So it's relatively easy to find security-oriented developers. They're not the cheapest, but on the other side, it will save you a lot of trouble in the future. Use always the latest version of tools, libraries, operating systems, and so far, and test a lot, and also test really malicious attacks. Don't just check everything is correct, check also what a hacker could do and see if this is 100% rejected. And also be prepared that your code has to be updated, and test if your first update really works. Otherwise you possibly delivered something which was intended to be updated, but when you need an update, suddenly it doesn't work. And then this is not really helpful. So this was the end of my presentation. I say thank you for listening to me. If you have more questions, send your comments and my questions to my address. You see here my email. And thank you very much and have a great day.